So we're going to go ahead and start this particular unit off by taking a look at overall structure. And I will admit that this first unit is a bit of a mess. It's kind of a hodgepodge because we're trying to catch people up that may have been long gone from OChem 1 and so need a little bit of time to kind of catch up with the individual content. And to be honest too, electrophilic addition is probably my least favorite section because it really is just kind of a mishmash of a bunch of kind of stuff and reactions, and it just comes across as just here's a bunch of reactions. So it's not my favorite for that. I will admit that the substitution elimination stuff I think is pretty cool. We're looking at useful reactions that get us very particular outcomes. And the big kind of overarching thing that's going to happen through all of OChem 2 is synthesis, which is ultimately looking for patterns. So when we talk about our electrophilic addition and our useful substitution elimination reactions, what we're really going to be trying to focus on is what are those patterns, because with those patterns, we can try and simplify the amount of work that we have to go through and do. So again, to our overview, synthesis, these are the basic steps in dealing with our synthesis reactions. So where's the position of our chemistry? Right? And that is kind of a difficult question because a lot of people have a hard time defining chemistry. So when I'm looking at chemistry, it's really referencing kind of two things. Structure, which is largely where electrons are located, but then the second part is then more specifically where electrons are located. So when we're talking about chemistry, we need to be thinking about structure as Lewis structure. And then once we have a Lewis structure, which does outline the bulk classification of where electrons are, we want to now nuance a little bit further and look at electronegativity. Electronegativity being a huge word to write out, you will see me write for the rest of the semester as the symbol chi, because that's, or I think that's the name of it. That's our symbol for electronegativity. So when we're thinking about chemistry, those are the two big topics that we're considering. Lewis structure, and then where is our electron density? And so the sooner that you can wrap your head around instantly drawing structures and instantly acknowledging differences in electronegativity to predict reactivity, the better off you'll be, and it'll be easier to go through and find those patterns. Okay? Kind of along those lines, the picture's been moving around because I didn't like where it was located. The next thing you'll want to focus on is where did that chemistry start and did it move in the process of your synthesis? So when you look at an overall reaction, you want to be considering those pieces as our big overarching symbols. The next thing you need to acknowledge is the reaction types. There are really 5 primary categories: acid-base, which in my class I focus solely on Bronsted-Lowry definition we call acid and base. You will hear a lot of organic chemists refer to Lewis definitions for acid and base, and it's not that those are wrong. Those are actually probably better definitions than our Bronsted-Lowry, but they're also really, really, really broad. So they apply to too many different things. So when you hear me say acid, I'm talking about a Bronsted-Lowry acid. And if you wanted me, or if I was trying to reference the Lewis acid, you'd hear me reference it as an electrophile. So that's where our primary differentiators are. Right? After that, we get our substitution reactions, our elimination reactions, our addition, and then our radical reactions, which do split out into substitution and not elimination, it's addition. So when you look at a reaction type, you need to decide which of those bulk categories you're in, or identify that category. Once you have that category nailed down, that can help you identify reagents. So instead of saying, what are all the reagents that I have to memorize, instead organize based off of reaction type, then you can organize based off of reagents, and sometimes that can help you move through it. Which then moves us to the next part. When we're looking at a reaction, we're looking at reactants and products typically. Think about the elements or atoms that are missing. Okay? If they're missing, those would have to show up in a reagent. And so that can help us move through a synthesis example. And then the last stage of synthesis is really an advanced one, which is consider or research, if you haven't thought about it or recognized it or have that content in the back of your head, complications of what you've guessed for an individual synthetic step. Right? So this means if you picked a strong nucleophile, are you saying it's going under SN2 dynamics, or is it SN1? So you would have to then kind of really nuance the levels of chemistry within those. That gets a lot more difficult because in a lot of cases you don't know what you don't know. Okay? And that's where you really need to get into the research aspect. So synthesis can be fun, treat it like a puzzle, but as a puzzle, you'll constantly have to refer back to the overall picture. Okay? When you get really good, you don't have to look at the picture. But when you're first learning puzzles, you got to go back to the big picture. Our electrophilic addition, I boil down into two big categories, and our textbook does the same. We look at acid additions, which is primarily chapter 11. I'm not going to talk a whole lot about those because those are simple because you're looking at acids, and in theory you've had a lot of practice with acids and bases. The electrophile addition, which is primarily chapter 12 and a significant chunk in chapter 24, becomes a little bit trickier, and we will spend some time looking at how I've categorized those. We won't spend a lot of time looking at practice for those. I'm going to look at the patterns that I see within it to help you try and think through and process that content. Right? What is that content? Now we're getting into kind of the nitty-gritty of OChem 2. You will be seeing spider diagrams throughout the entire semester, right? And that's a lot of what OChem 2 is. New mechanism, here's 20 reactions. You need to know those reagents. One of the things that can become daunting is people spend too much time memorizing the reagents, but not the secondary aspects, the structure, and the electronegativity. So if you can remember that structure and electronegativity as you move through, that can help you memorize better so that you understand where things are going and why things are doing the things they're doing in each of these reactions. All right? This first one was largely our chapter 11, chapter 12 kind of splits that difference. And a little bit of chapter 25 when we're looking at radicals. Then we get our alkene oxidations, which I would argue are still kind of in that electrophilic addition type mechanism. And those are largely in chapter 24. And in fact, in our book, it's like a section of chapter 24, and they really just treat it as a bunch of reagents. Right? So again, if you need help reviewing those, that's cool. You're going to have to dig probably back to your OChem 1 stuff, and I've got tons of OChem 1 stuff available online that you can go through and look at for those details. Alkene or yne reduction. We've got a lot of reduction reactions. These fall in, I think, chapter 13 for our textbook on how we go through and reduce the varying nonpolar pi bonds. When you go through and look at reagents, look for ways that you can group things and disgroup things. This group didn't really sound to make much sense, but really what we're saying is how can we pull that information out and point it out as different? So one of the things that you might note when you go through and look at this one is that these over here are a little bit different, because when we look at the alkene and the alkyne going to the left, they end with alkanes. And if we look at the ones going to the right, we're not ending at an alkane, we're ending at an alkene. So the chemistry is a little bit different. Okay? By acknowledging that that chemistry is different, that can help you categorize those as a memorize those, and then assume when you see the other reagents that they just do one big thing, alkanes. Okay? So that way you don't have to memorize each of the reagents, you just have to memorize where there's big differences. The other thing to note within this is that you'll see a cis result versus a trans result. And it turns out that that cis result actually categorizes very well with the rest of the reagents, and that hydrogen adds to the same side of the pi bond. The trans result is way, way outside the realm of things, which means that is one that is very commonly thrown at you on tests because it stands so far outside of the realm of normality that you really need to commit it to memory because it's so drastically different. Okay? And it's those big differences that you're trying to find to really centralize your memory on. And then we get some, well, this is just looking at the mechanism for that last one just because it's neat. We will look at this mechanism not in the reduction of an alkyne to the transalkyne, because there's the mechanism. It's neat because it's known as a radical anion, because when you go through and look at the mechanism, you have radicals, unpaired electrons, and anion, a negatively charged carbon. So we end up with an intermediate that has both. That's why it's called a radical anion mechanism. So this mechanism is neat because of those details. Really, the mechanism itself, you probably don't need to know. You really need to know that trans differentiation. Where it's going to become more important to kind of address how the mechanism works is when we get to the end of the semester. And so it's not going to show up in this unit, but this reaction here is kind of a forecast, if you will. So this is only going forwards, not yet. I'll reiterate that, that this reagent is so powerful as a reducing agent that it can reduce a benzene, which is pretty bizarre. Where the mechanism becomes important is that when you substitute that benzene, you get different results. Okay. Then we get our useful substitution and elimination, which I believe is the end of our overview. So again, here's all of our reagents to look at. When you think back to your substitution and elimination from OChem 1, you probably noted that you didn't deal too much with stereochemistry being very particular. Okay? Well, that's the thing that's kind of useful about our reactions, is that we get one product. So the SN1, where we produce two products, isn't as useful because we get lots of products. Here, we're getting one product. So very, very particular in the reagents, and that improves the odds. The other thing that we'll see within that particular chapter is this bottom one. So an interesting elimination reaction. Again, interesting. As soon as you hear that word interesting, you should be committing it to memory. We're getting the non-Zaitsev or anti-Zaitsev. Anti-Zaitsev is a bad term. Non-Zaitsev makes more sense. We're getting the elimination happening where we would not predict it, right, according to stability. So that's interesting. And then we will also see a large part of this chemistry over there are tautomerization or enolate chemistry. Tautomerizations, as much as people, I'm pretty sure I butchered the hell out of spelling that, as much as students dislike that chemistry and try to ignore it, that is 90% of OChem 2. That's a bit excessive. 60% of OChem 2 is tautomerization reactions and how those reactions produce very reactive species that can then cascade out to other things. It also contributes to probably 30 to 40% of the chemistry in biochemistry. So if you were going to take a biochemistry class, that enolate structure becomes really important because it explains a lot of the biochemical pathways that you would study in biochem. And with that, I think we've covered our big overview, but just in case, yep, we're good. So we'll go ahead and say thanks for listening to the overview. That's not the right stop button. Let's try that.